Hi everyone and welcome to this new video. In this video we continue our discussion over binary exploitation foundational topics, and in this video specifically we will talk about stack frame and the roles of two specific registers, which are the RSP, which is a stack pointer, and RBP, which is the base pointer. So in the video I brought a very simple piece of code that will allow us to explore the concept of stack frame, what is a stack frame, what is the role of the RSP, and what is the role of the RBP. And this will allow us to understand what is a function Prologue and a function Epilogue. And finally, we will talk about the call stack. As always, I hope this video is useful to get you accustomed to these ideas. If it is, leave some feedback, subscribe to the channel, and share this video with like-minded people to help me grow. That's it, enjoy the video. So let's start by reading this really simple example code. So here we have a C function that defines a main and a hello function. So the main function takes a pointer to a string. Now this is an hard-coded string, and when you program in C, if you have a string like this, these are read-only strings. This means that they are located in the memory of your process, but you cannot modify them, you can only read them. And then we call the function hello with this particular pointer. In the function hello, we define a local variable 42, which is called age, and then we just print it out in the standard output. Hello, we put the name, your age is, and we put the age. So we can go into the source folder, we can create a hello.c, and here we say source hello.c, and here we paste this code. And then we compile it with GCC to obtain a 64-bit ELF binary. And at this point, we can debug it. We can debug it with GDB. So let's open a new window here and let's do gdb-q hello. Now, when we open with GDB, we can disassemble the functions. If we do info functions, we get the main function and the hello function. We can disassemble the main with the disasmain, and here we get the code for the disasmain function, which is written using the Intel notation. And we can also obtain the disassembly of the hello function, which is also written using the Intel syntax. Now look at what we have here. We have two different functions and we have the assembly code for those functions, for the implementation of those functions. Now, even though they are different functions, they actually share a lot of similarities. For example, consider the first three instructions of main and of hello. We have in both main and hello, we have a push RBP, so we are saving the value of the register RBP into the stack of the process. We do a move RSP into RBP, so we are moving the value of RSP into the register RBP. That is, we are changing the value of the register RBP. And notice that before we change the value of RBP, we have saved it into the stack, and we save it into the stack so that later we can retrieve it. So that's the idea. So we have a push RBP, then we have a move RSP into RBP, and then we have a sub of a certain amount. Now this thing change depending on the function, but we sub this from RSP. So RSP here is the same, it's just that the amount of bytes we subtract to RSP changes. In the main function, we subtract 0x10 bytes, which is 16 bytes. In the hello function, we subtract 0x20 bytes, which is 32 bytes, because we're talking about hexadecimal. So, different function, but we have the same instruction at the beginning. And not only at the beginning we have the same instruction, also at the end. Look at this, at the end, both in main and in hello, we have this common pattern of the leave instruction and the ret instruction. So this is another common pattern. This is to say that functions behave similarly, because at the end of the day, the compiler treats any function as a general function, so it will behave similarly with respect to all the different functions it encounters. Now notice another interesting behavior. So, as we showcased in the previous video here, before the various calls instruction, we move values into the registers. Because when we're talking about x86, 64, So a 64-bit architecture, we said in the previous video that arguments to the functions are passed through registers. So the calling conventions wants that the arguments are passed through register, and that's good. However, what I want to showcase is that look at the various memory accesses that we have here. We have a bunch of memory accesses with this following pattern. We have RBP minus a certain amount, and then we read that value from the memory, and then we do something else. We can either overwrite it with a register, or we can just read it and put it into a register. But the pattern is RBP minus a number. And in this video, we will understand why we have this common instruction at the beginning and at the end of every function, and also what is the role of RSP, what is the role of RBP, and why do we have this common pattern to access the memory of the form RBP minus a given number. Now, to make sense of this, let's start by talking about stack frames. Now, a stack frame is a data structure, and this data structure is used to store information about a specific function call. It is used by the processor during the execution of a program. So anytime in our code we find a function call, like this one, like hello, and then we have the arguments of name. Now this is a function call. So the processor has to do a bunch of things to make this happen. And in the previous video, we saw how the processor handled the arguments of the function. Now, the arguments are a very specific thing that the processor has to take care of. In general, for handling a bunch of different stuff, we have the concept of stack frame. Now, a stack frame for a given function typically contains the following information: the return address of the instruction to execute after the function returns. This is because at the level of the assembly, when I jump into a law, like when I'm here, I jump into this, then I execute the instructions like this, perfect. At some point, however, I have to ask myself, the processor has to ask himself, or I guess itself, this question. Okay, cool, I've executed hello, but now where do I return in the code? Who called me? What is the next instruction to execute? And essentially, for example, if it was main that called hello through this call, then at the end of hello, the next instruction actually has to be the next following the call. So in this case, it will be this move EAX00. So that's the idea. It's main plus 31. It's the instruction at this specific address. So the processor has to understand this information. Where is this information stored? It is stored in the stack frame. And basically this is why we need to save the return address into the stack. But we don't have only the return address, we have also the function arguments. So these are the arguments passed to the function call. However, remember that in the last episode we saw that the arguments are passed through registers. Now, it can happen that the processor passes the arguments through registers, but then the function saves the values of those registers into the stack. So even though initially they're not into the stack, they are saved later on. And most importantly, like the most usage of the stack frame is actually for local variables. So anytime you define a local variable, the place in memory where this local variable can live is in the stack. So for example, in the example code I showed, when we define this age42, this hello function, well, if we check the disassembly code here, essentially, now 42, what's happening is that this is the instruction that initializes the 42 value. Because look at this, here we have an hexadecimal value of 0x2a. Now, if we print this into decimal, 0x2a, we get 42. So that move instruction, this plus 12 instruction, is the one that actually initializes the variable. Now, this value is written into a specific area of memory, and the area is given by RBP minus 0x4. So within the memory of the process, this value is written in a very specific area, and this area actually belongs to the stack frame of the function. Now, to manage the stack frames and the stack in general, two registers are used, RSP and RBP. These are the main protagonists when it comes to the stack. So we have to imagine that the stack is a typical stack data structure used in computer science. So we have blocks of data, right? And each block is a stack frame. So a stack frame. And each frame contains the information about a specific function call. So this is important to understand. For example, if I have a recursive function, so a function that is defined in terms of itself, when it actually executes, like for example, let's make a really simple example, like let's do factorial. So factorial of n is defined as n times factorial of n minus 1. And if n is equal to 1, this is just gonna be 1. Else, this is just gonna be this. Actually, I believe it's 0. If factorial is 0 is 1. So this is a typical recursive definition of the factorial function. Now, when I call this function, for example, I say factorial, I'm just gonna write f for brevity. I'm gonna say factorial of 5. This is a function call. It will generate a stack frame. So in my stack here, I will have a specific stack frame for f of 5. However, in the definition of f of 5, this is actually going to call f of 4. So this is going to call f of 4. And for f of 4, a new stack frame will be defined. And then this is going to call f of 3, and a new stack frame will be defined. So the important thing to realize is that we have for each function call a specific stack frame, even if we are talking about the same function. And each stack frame has all the local information about that very specific function call. So let's now talk about the roles of these registers which are used to handle the stack. Let's start with RSP. Now the stack pointer, also known as RSP, is used to keep track of the top of the stack, which is the area of memory that represents the boundary between the used stack and the space still available. So remember this thing. In x86-64 architectures, the stack grows downwards. It means that it grows towards lower addresses. So in our memory address, when we want to grow the stack, when we want to have more space on the stack, we actually do not add the RSP value, but we subtract it. And we subtract it because the stack grows downwards. Because, for example, if here I have higher addresses and lower addresses, right? So let's say essentially, for example, let's consider this. I have this situation. So the RSP right now points to this specific address. This is just a memory in the area. This means that all the area from the RSP to the end of the stack memory segment is actually used by the stack. So this is valid stack memory. So it is memory and is going to be fragmented into different stack frames, right? So this is completely valid stack memory. Now, anything that is lower than the RSP value is not used yet. So this is like unused memory. It is available memory for future use. Now, when we do this instruction like sub RSP 0x20, 0x choose 0, which we find, for example, in the hello function. So look at this. Here we find a sub RSP 0x choose 0. In main, we find a similar thing, but it's a little bit, the value is lower, 0x10. Now, this kind of operation is done to grow the stack, to include more memory for the local variables of that particular functions. So if you have the RSP that points to this address that ends with E410, and then we grow the stack by 0x20, which is 32 bytes, then the result of this operation is as follows. Previously, the stack pointer pointed to this. Now, the stack pointer points to this. All this area is now memory for new stack frame. So this is memory for the new stack frame. What we can put here, we can put arguments, we can put local variables, we can put a bunch of stuff. So when you are analyzing a piece of code and you see this kind of instruction like sub RSP with a given value, do not worry. You are just growing the stack. You are growing the stack by a certain amount, and this amount is computed by the compiler depending on the local variables that you will use in your function, and also depending if you want to put the arguments within the stack. Because, for example, look at this. So, look at what happens. In main, we put the arguments into the RDI register, so the pointer is written into the RDI. But then in the function, we grow the stack by 32 bytes, and then we write the pointer of the string, which is the argument, into the stack. Which means that even though technically it's the registers that are used to pass arguments from one function to another, when the function receives the arguments, the function can still decide to put them in the stack frame, which is what happens here with this move operation, with this like RDI writes into the stack frame at this particular offset. Now, why do we use RBP? Now, what is the role of RBP? Now, let's discuss now the role of RBP. Now, the base pointer, which is RBP, is used to access the stack frame during the execution of a call. The presence of the base pointer is useful because the stack might grow or shrink depending on the different execution paths taken, while the base pointer remains fixed for the entire duration of the function. So let's go back to this code and try to understand now what happens to the RBP value and how it is used. So before the call, before this instruction, the stack situation can be as follows. So we have the stack frame, so we have stack frame of main. So here we have all the stuff of main, perfect. Now, the call instruction happens, and when we have the stack frame, it means that the RSP now points here, and RBP points at the base of the stack frame, points at the beginning of the frame, which means that by using RBP, we can offset anywhere within the frame. Now, when we do the call to hello, what happens is that, okay, we're gonna save RBP. So RBP is actually saving to the stack. So we put here the old RBP. And so we move RSP into the next location. Perfect. Now, look what happens. Now we do a move of RSP into RBP. So we are changing the value of RBP. And now the new RBP will point to the RSP. So RBP now points here. So now RBP does not longer point here, but points here. And then we do a sub of RSP 0x to 0. So we increase RSP by like 32 bytes. So RSP now is here. So look at what happens now. Now we have a new stack frame, but this stack frame is not for main anymore, but it is for hello. So now here I can put all my local variables, I can put all my arguments, I can put whatever I want within the context of hello. And basically this is why every function has the same instruction at the beginning, because the objective of those instructions is to save the value of the previous base pointer, update the base pointer to the stack pointer, and grow the stack by a certain amount. Now, once we set up the new stack frame, once we have got the value of the new base pointer and we have grown the stack, at this point, what's the idea? Well, the compiler knows that the base pointer register, the RBP register, will always have the same value during the entire execution of the call. Therefore, it becomes an extremely useful point because it's going to represent the base of the stack frame, and if I want to access anything there, I can simply use those offsets. And why in here do I use minus values? So I do minus offsets because, as we said, the stack grows downwards, which means that if I have to access an element which is like in this location within the stack, I do not have to add, but I have to subtract a certain offset. And the cool thing of RBP is that since it never changes during the entire execution of the function, it will always have the same offsets. So the same variable, for example, the first local variable or the second local variable or the third local variable, they will always be accessed using the same offset. For example, look at this. By just looking at the code, we can see, okay, here I have two things that I take from the stack frame. One at offset 0x18 and one at offset 0x4. Now, the one at offset 0x18 is written from RDI into the stack frame. this is gonna be clearly the argument of the function, which is taken from the register and written into the stack. This instead is seems a local variable because I have initialized with an hard-coded value and I've put it into the stack. Then those two elements are written into the various registers, and then we call the printf functions. So even though I cannot look at the C code, but just analyzing these memory accesses and the fact that I use 2 times the same offset, here I know, okay, this variable is the same as the one before, because during this execution, the stack can grow more eventually, but the point is that the base pointer value remains fixed within this call, and even if I call another function, the operations that happens at the beginning and at the end will restore the correct value for the base pointer. So I can just abstract them away. I don't care here if I have different calls, because every time I have a call, at the end of the call, I will have nullified the operation on the base pointer, because the base pointer is always restored at the base of the current stack frame, of the function I'm analyzing. And if you apply the same reasoning to the main function, here you can see that actually here we have one local variable, which is at offset RBP minus 0x8. So this is the offset in the stack frame that we find the local variable. And indeed, if you analyze the code, remember, within the main, we just have a local variable, which is a local car pointer. And in the low, we have a local variable age and an argument name, which is a car pointer. Now, even if you consider a more complex example where I introduce a variable young1 if the age is less than 30, and I just have some conditional printing, and I analyze the disassembly code here, do you notice the pattern, the memory access that is used to deal with the stack frame? Well, look at this. We grow the stack by 20 and we put the new base pointer, as always. Then here we have 3 different offset. RBP minus 0x18. So this is the argument. Then we have RBP minus 0x8. So this is a local variable. And then we have RBP minus 0x4. So this is another local variable. And so this means that when you see this RBP minus stuff, it's always either local variables or arguments from the functions, from the function definition essentially. And this is to say that anytime you see memory accesses like the following ones, where you have RBP minus an offset that is repeated throughout the function, well, you can be sure that most of the time, if the code was just compiled through a normal compiler without obfuscation, well, those are local variables, or they can be values taken from the arguments. And here I put essentially what I was mentioning before. So basically that's the idea. And so at this point we can actually understand the prologue and the epilogue. So the function prologue, actually we already discussed it, and it is made by the following 3 instructions, and here I wanted to include the 4th one as well because it makes sense to include. But technically speaking, I believe that with function prologue we only refer to these first 3 instructions. So basically the idea is that with a push RBP we are saving the old base pointer to the stack so that later it can be recovered. This is key. And since at this point the base pointer value is used to determine the stack frame of the caller, so at this point of the call, we did not update the RBP or the RSP, which means that we are using the value of the previous stack frame, of the function who called us. So we are saving that into the stack. Then we are modifying the base pointer with the stack pointer, and this is used to prepare the stage for creating the space for the new stack frame. So we are saying, okay, now I'm gonna move the base to the last address that I'm using with the RSP, and then I'm gonna grow the stack. So this with the sub RSP, the stack grows downwards, so we subtract from RSP and we create the space for the new stack frame. And after we grow the stack, we can actually write the argument that was passed to the RDI register through the RDI registers. And so now we can understand why we have these 3 common instructions. Of course, since growing the stack depends on the kind of local variables that we have, on the kind of arguments that we have, different functions will grow the stack by different amounts and will use different values in the stack frame. I mean, this makes sense, right? So what about the function epilogue instead? So we can now understand the function epilogue, which is made up of the following two instructions, leave and ret. Now, the leave instruction, which seems atomic, can be described as follows. So two different things happen. The first one is a move of RBP into RSP, and this is used to restore the stack pointer to the base pointer. Essentially, this deallocates the stack frame used by the function, because at this point in our execution, what we have is that here we have the RBP, and here there was the RSP, right? When we do this write RBP into RSP, we are essentially saying, okay, RSP now becomes this one, RSP. So this point both RBP and RSP. So we are deallocating all this space. Now this space is no longer used. And if we call a different function, it's going to be allocated for the new function. So this deallocates the memory. Then, if we remember well, at this point, what do we have in the stack? Well, the next value that we have in the stack is the old RBP value. And this is why we do a pop RBP. So a pop RBP will take the value at the top of the stack and will write it into the RBP register. And this is used to restore the base pointer of the caller, that is, of the function who called us. Because before, it was actually pushed into the stack. I mean, if we remember here what we do in the prologue, well, we push RBP, and therefore it only makes sense that we pop it at the end. Now, the ret instruction instead implements a simple pop RIP. So we are popping the value in the stack into the RIP register, into the RIP register. Now, this is the instruction pointer register in 64-bit architecture x86-64. So why is it very important? Because at this point with the ret, we are gonna restore the execution flow to the next instruction of the caller function. So here, remember the issue, right? We call hello from main. After hello is done, we want to come back to this value, to the next one, here, to this one, to main plus 31. But how do we do that? I mean, in hello here, we do not have any information. So once again, the stack is used to convey that information. Indeed, one of the things that call does is actually push the value of the next instruction into the stack. So we are pushing the value of the next instruction into the stack. We are sort of doing like a push RIP. Of course, we cannot do this directly in the assembly because the RIP register is not available through the ISA, and this is done for security reason. We cannot control it directly. However, we have these call and ret instructions which implicitly let us control the RIP register, the RIP register. So, and the pattern here is very similar because anytime we put something, we have to pop it. The problem is that we see the push, we see the explicit push in this case. The pop is implicit in the leave. So the leave is used to restore the base pointer. And when it comes to call and ret, here we do not even see the push RIP and we do not even see the pop RIP. But essentially, call will push the next instruction into the stack. And at the end of hello, after we recover the value of RBP, we can also recover the value of RIP, of the instruction pointer, which will point to the right instruction. And this brings us directly to the call stack, because the call stack is obtained by having a sequence of stack frames. It is essentially the stack of the program. It is managed in a LIFO approach, last in, first out. It means that when I do a call f, I create a stack frame for f. When this function calls a g, it's going to be created on top of it a g, and then as soon as g is over, it's going to pop this one. So the last that was in is the first going to be out. So basically that's the policy. It's a typical stack policy LIFO, and we can actually print this information with GDB. For example, if here I put a break into hello plus 44 and then I do a run, and here I say, for example, BT, here you can say, look, this is the call stack. You started from main and then you called hello, and these are the arguments. Now, to make a more interesting example, actually, here I have a different example, calls.c, in which we have a bunch of different functions that call each others. Now, for example, the function c is called by the function, let's see, So here we have function A, which calls function B, which calls function C. So function C is called by B, which is called by A, which is called by main. And with this example, we can see more stack frames. So we can compile it as simple as this. So we can do calls.c, and then we can do gdb-q calls, and then we do this as function C. I'm going to put a breakpoint in function C, plus 39, and then do a run. And here, if I do bt, look at this now, the call stack is a little bit more complex because I have the frame for C, the frame for B, the frame for A, and the frame for main. And they are one on top of another. So essentially, this is the idea. And this is also why buffer overflows are dangerous. And this is why it is possible to do binary exploitation over the stack. Because if you have a buffer overflow into the stack, this allows you to modify this metadata that is written by the processor, such as the saved instruction pointer, the save return address essentially. If you are able to modify such value, we can hijack the control of the program to execute different instructions at an address that we want. So with BT, we can print out the call stack. If you want more information about the single stack frame, we can say info frame and then the index. For example, with this, we have that the stack frame, the address in the stack, it is called by frame at the other stack frame, which is 1 essentially. So we have the argument list and we have the local variables. And here we have the saved registers, RBP, RIP. So basically that's the idea. And with all this information, we can reconstruct essentially the flow. And so this is it for this video. In this video, we analyze what are stack frames and what is the role of the registers RSP and RBP, of the stack pointer and of the base pointer. And so next time you see a disassembled code with this function Prologue or function Epilogue, hopefully now you know what they mean and you know why they are implemented like that. I hope the video was interesting. In the future, in this series, I plan to do more practical exploitation examples to make it a little bit more fun. But that's it for this video, and to the next video.